So today we're going to take a look at calculating the pH at the equivalence point when titrating a strong base into a weak acid. So we're given the concentration of our weak acid. We have 25 milliliters of 0.15 molar acetic acid. And we're asked to calculate the pH of the solution at the equivalence point when we titrate 0.1 molar sodium hydroxide, and we are going to take the pKa of acetic acid to be 4.75. So here we're given all the information we need to solve this problem. The first step we need to do is find out how many milliliters of base are going to be required to reach the equivalence point. So if we're starting 25 milliliters of acetic acid, I'm going to abbreviate acetic acid as HA for the acid. 1 liter of HA has 0.15 moles of HA. And with this particular acid and base, it's going to be a 1-to-1 ratio of acid and base for the neutralization reaction, which means for every 1 mole of acetic acid, it will require exactly 1 mole of NaOH to neutralize it. So 1 HA is equivalent to 1 NaOH. Next step is going to be to put our concentration of the NaOH in here. So we have moles of NaOH on top, which means we need moles of NaOH on the bottom. So you have 0.1 mole of NaOH is equivalent to 1 liter of NaOH. So now, when we multiply this through, we're going to notice that first our volume is going to cancel. We're going to be left with moles of acid, and then moles of acid is going to cancel. We're going to get moles of base, and then moles of base is going to cancel. We're going to end up with a volume of base. And what we find is the equivalence point will be reached when we get 37.5 milliliters of the 0.1 molar NaOH, which is equal to 3.75 millimoles of NaOH. Okay, so now that we found out how many milliliters of this solution of base is required to reach the equivalence point, now we are prepared to begin solving for it. So we're given the pKa here, and we're going to need to go from the pKa to the Kb here. And the reason for that is because originally when we had the acid in solution, we're calculating pH, we're calculating the reaction of HA plus H2O is going to form A minus plus H3O plus. Now, because we've reached the equivalence point, we have used up all of our HA in solution, which means now we're looking at the reverse reaction. What we're actually looking for is the equilibrium constant for A minus plus H2O is going to form HA plus OH. So this is what we're looking for now. So if this is Ka, it represents the equilibrium constant for the first reaction, which Ka is 10 to the opposite of pKa. Then the second reaction is going to be represented by Kb. So we can solve for Kb if we have Ka. So something you should have learned in your chemistry class is that Kb and Ka multiplied by each other are equal to Kw. And Kw is a constant. It's the water ionization constant, and it is equal to 1 times 10 to the negative 14th. So these are equal to 1 times 10 to the negative 14th when they're multiplied by each other. So if we wanted to solve for Kb here, we could just divide Kw by Ka. So if we solve for Kb, we find that Kb is equal to Kw over Ka, which is equal to 1 times 10 to the negative 14th. And Ka is going to be 10 to the opposite of pKa, which is 4.75. When we go ahead and solve for this, we're going to find that Kb is equal to 5.62 times 10 to the negative 10th. And this is Kb. So the next thing we need to do now is to set up an equilibrium expression. So if we have our reaction here, the second one that we're looking at, these are going to be our products on the right side. So the K of a reaction is equal to products over reactants. So Kb is going to be equal to the concentration of HA multiplied by the concentration of OH minus. Now these are going to be equal to each other because it's a 1-to-1 ratio with the formation of the products from the reactants. And this is going to be over the concentration of A minus, which is what we're starting with, our product. So what that's going to look like here is we're going to do 5.62 times 10 to the negative 10th is equal to, now I'm going to substitute the HA and the OH for X. And because they're equal to each other and they're multiplied by each other, X times X is X squared. And then we know what A minus is. A minus is going to be this number of millimoles, because that's the number of millimoles of HA we started with. We reacted it all with strong base, so now we're left with this many millimoles of A minus, 3.75, but our volume has changed. So no longer do we have a molarity of 0.1 molar or even 0.15 molar. We have to find out what our new concentration is. So molarity is equal to the number of moles over the volume. So we have 3.75 millimoles of A minus. And now our new concentration is going to be 25 milliliters plus 37.5 milliliters. Now, when we divide this out, we're going to see that milli cancels out, and we're going to be left with moles per liter. And this is going to be 0.06 molar, and that's our concentration of A minus. So the concentration of A minus is going to go in the bottom here. So we have concentration of A minus in our equilibrium expression. It's going to go down here. So we got 0.06 molar. All right, now we just need to solve for X. So we're going to multiply this out first, which will give us 3.37 times 10 to the negative 11th is equal to X squared. And now to solve for X, we're just going to take the square root of each side, and we are going to find that X is equal to 5.81 times 10 to the negative 6th molar, and that is equal to X. Okay, so this is going to be equal to our concentration of OH minus. Now we are asked to find the pH here. The pH, if you remember the equation for pH, is equal to the opposite of log of the concentration of H plus. So there's two ways you can go about going from concentration of OH minus to the concentration of H plus. We can either go through the water ionization constant route, or we can just simply say that the pH is equal to 14 minus the opposite of the POH, which is the opposite log of the concentration of OH. POH is equal to the opposite of log of OH. So if we do 14 minus the opposite of log of 5.81 times 10 to the negative 6th, we find that the pH of this solution is equal to 8.76. And that is how you find the pH at the equivalence point in this particular problem. Thank you for watching.